really have also time for the question and answer session in the end. So yeah, welcome. We are two specialist groups who actually joined forces for this webinar. The water reuse group and the integrated modeling and integrated assessment group. And yeah, I'm very happy that this came together. And it's about bridging the gap between the water reuse community and the model developers, actually. My name is Marion Schneider. I'm a postdoc at TU Ghent. And my topic is on monitoring and control of water reuse systems. And I will guide you through today's seminar. So what will be on today? We have a very, very brief introduction to the two specialist groups. We are really happy that both chairs are actually here. So Elena Torfs and Josef Landsteiner from the water reuse group. Then the first speaker will also be Josef Landsteiner to give us an introduction on water reuse. After that, Giacomo Belandi will give an overview over process models, and then Eberhard Morgenroth will talk about microbial risk assessment and why this is important for water reuse. And then in the end, Luca Panzerini will talk about impact assessment models, and we will have question and answer sessions. So please keep your questions and comments to the end. Then I wanted to inform you what you have seen already, that the session is being recorded. We will also put it online then, so that our colleagues can watch it later on. Please don't use the chat function. Use the question and answer section instead. So we would very much appreciate if you could do that. It's much easier for us to moderate, but we could not block it. And please keep microphones and cameras off. However, for the question and answer session, we actually encourage you to raise your hands, and we will then call you one after the other so that you can basically see each other, because I mean, our goal is to bring two communities together. So we also appreciate if you see each other's faces when you ask questions and discuss. Okay, so that's for the introduction. I would like to hand over to Elena to introduce the modeling and integrated assessment group. Elena is actually a professor at the University of Laval. She is the chair of the modeling and integrated assessment group, and she has experience with all different types of models. The floor is yours. Thanks.
Can you see my screen, Marianne? Okay.
Yes.
So yes, hi, welcome everybody. I just want to very briefly present who we are for those that don't know the MIA specialist group. So my name is Elena Torfs, and together with Saba Daneshgar from Ghent University, I chair the MIA specialist group. So MIA stands for Modeling and Integrated Assessments. And that brings us also to the focus of our group. So we really want to facilitate the use of models and different computing tools to support understanding, management, and optimization of water systems. And the keyword here is really water systems. So it can go from very small scale unit process to really very big interconnected scales on a city level, on a region level, and see how modeling and digital tools, computing tools can help in analyzing these systems. So what we try to do is, first of all, stimulate interaction and knowledge transfer in the domain of modeling and integrated assessment between different stakeholders from academia, industry, and so on. This webinar is one way to do that, and also to interact with other specialist groups and find synergies there. And also there, I'm very happy with the webinar today because we've actually managed to connect with the water reuse specialist group and have this joint event, which I think is very, very nice. A little bit something about our activities. We've historically always had a lot of active task groups and working groups. And in the last years, a number of those task groups have published scientific and technical reports that can be found on the website of Iowa Publishing on good modeling practice, on design and uncertainty, on physical chemical modeling, on modeling for greenhouse gas emissions. So all these STRs are available for you to consult if this interests you. We still have a number of of active working groups at the moment on integrated urban water systems, computational fluid dynamics, on good modeling practice, and a new group that recently started on hybrid modeling, so combining process knowledge models with more AI and data-driven tools, for which Marianne is actually the chair who is here. Also, our active task group still, one on membrane bioreactor modeling and control, and one on the continuation of good modeling practice, since modeling keeps evolving. So this is still a relevant task group. If you want to know more about any of these groups or their activities, I invite you to go to our Iowa Connect page and reach out to the people involved. We have two very core specialist conferences from our group. One is the Watermatics conference series about modeling and integrated assessments. We just had finished the last version. This is a 4-yearly conference, which was in Quebec. But mainly, there will be a special issue coming from the content of this conference. The deadline is today to submit, so soon this special issue will be available. So keep your eye open for this. And then we have the water resource recovery modeling seminars that are every 2 years. The next one will be now in April in USA, in Notre Dame, Indiana. And the one after that, we just recently decided on the location, will be in Barcelona in Spain in 2026. What is not on this list is the next Watermatics conference, which is for 2027, where we will soon launch the voting for the location. So that's a brief overview of who we are. If you want to learn more, you can find us on different social media, Iowa Connect Plus, of course, LinkedIn, Twitter, and we also have an open website where you will find all information about our events and news. So that's it for me. I will give the word to Joseph Dan to introduce his specialist group.
Okay. Thank you, Elena.
So I think I will use the moments until the slides are here. So Joseph is actually the chair of the water reuse group. He has a lot of experience in water reuse. He works for WABAG, and I'm very happy to hear your introduction to the specialist group as well as your presentation afterwards.
Thank you, Marianne. The Water Reuse Specialist Group is globally the leading forum in water reclamation and reuse, and is the largest specialist group of IWA. Our major aim is the implementation of safe water reuse practice through the promotion of successful water reuse projects and sharing of information via our international knowledge network, specialist conferences and website. We had so far 13 conferences. The last one was in India. The next one will be in South Africa in 25. And in Q4 this year, we will have a call for the 15th conference, which will take place in 27. We had also a webinar series. We called it On the Road to Chennai 2023. 4 webinars. For example, water use in the USA, a trend on the rise. The recordings of these 4 webinars can be downloaded from the IWA website. 1 year ago, we had in Chennai, in India, the 13th conference. It was a very successful conference. And next year, in March 2025, we will have the 14th conference in the beautiful city of Cape Town. And if you're interested in water reuse, I would cordially invite you to join this globally most significant water reuse event. The call for abstracts will be end of February, submission deadline beginning of May. And we publish, of course, also newsletters. You can see 5 newsletters here, which can be downloaded from IWA Connect Plus. The next one will be published in February or March. And last but not least, we have working groups. If you're interested to join a working group, just send an email message to Samendra, our secretary. Yes, that was a short introduction. I thank you for your attention. So, yes, can you see the presentation?
Yes, we can.
Thank you. Yes, I will give you a brief overview on water reuse. I start with an introduction, then I will address an Indian case study on industrial reuse. After that, I will provide you with an overview on potable reuse projects. Then I will present the Windhoek case study, and then I will draw some conclusions. The drivers for water reuse are mainly, the most important one I would say is water shortage caused by climate change, population growth, urbanization, industrialization, and developing and emerging economies. There are, of course, economic reasons, for example, lower freshwater demand, lower energy demand, e.g. the transport from distant sources can be very energy and cost intensive. Very important, there is a boost in water supply security. Used water or wastewater is a drought-proof resource. Last but not least, policies, regulations, guidelines. For example, the EU regulation on minimum requirements for water reuse adopted in May 2020, or the treated wastewater reuse policy for Tamil Nadu, India, issued in November 2019. First case, Chennai, city of Chennai is the capital city of Tamil Nadu. It's located in the southeast of India on the Gulf of Bengal. They had in 2019 a severe drought. The summer monsoon appeared to fail. It was the worst drought in history. Freshwater reservoirs were empty for drinking water production. It was a state of emergency comparable to Cape Town. Day 0 was very close. Drinking water had to be supplied by government tankers. Now I come to the Coimbatore water reclamation project. The Coimbatore water reclamation plant, for example, in this blue building, there are housed the ultrafiltration and reverse osmosis units, capacity 45,000 cubic meters a day. The reclaimed water is reused in various industries. The raw water is secondary effluent. Here you can see the main design parameters. Total dissolved solids 1,500 in the raw water, less than 70 in the reclaimed water. Total silica 40 in the raw water in the secondary effluent, and less than 5 in the reclaimed water. It's a contractual standard. The aim is to boost the overall supply security in Chennai by industrial reuse. The reclaimed water is reused at these locations. Here are industrial clusters, and the advantage is, the benefit, these freshwater reservoirs can be saved for drinking water production. a simplified process flow diagram of the plant. As mentioned, the robot is secondary effluent from the nearby Coyambedo sewage treatment plant. We have pre-treatment by chlorine dioxide dosing for pre-disinfection and slight oxidation. Then dual media filtration, ultrafiltration, reverse osmosis, antiscalant dosing, and so on, degassing unit, ozone disinfection, and distribution by a 60-kilometer long network to various industries. This slide shows the ultrafiltration unit from Inge company, reverse osmosis unit from Dow, as mentioned, capacity 45,000 cubic meters a day of reverse osmosis concentrate, permeate, and removal of silica, very important parameter in industrial applications. In order to avoid scaling, it has to be removed. In this phase, 25 milligrams per liter, and in the RO permeate, only 0.3 milligrams per liter. It's the standard, the contractual standard is 5 milligrams per liter, so it's excellent performance. However, or nevertheless, an R&D project is conducted in order to further improve the performance and for OPEX reduction. And operating intelligence tool from the Canadian company Pani Energy is used. This tool interacts with the PLC and SCADA system and helps to improve the quality of higher impact decisions that need to be made by the plant operation team. The tool provides consultation of the O&M team, guidance, prioritization of issues, data management. In the next slide, you can see issues, opportunities, value, and cost savings. For example, one issue is at present the suboptimal membrane service timing through scheduled cleaning procedures. This tool is in the implementation phase, and the opportunity will be started up in 2 months. The opportunity is that a predictive model provides recommendation for optimized membrane cleaning. The value is then longer uptime, longer membrane life, chemical and energy savings. Another issue is the reactive, that means non-proactive problem detection through alarms. The opportunity is that an expert system with automatic fault detection and diagnostics provides recommendation for proactive intervention. The value will be longer uptime and savings in equipment and troubleshooting time by predictive maintenance. At Coyambedo, there is another pilot project. It's RO concentrate treatment. Brine management or concentrate management is gaining in importance. The authorities request the treatment of RO concentrate, and the aim is in this project the removal of recalcitrant COD, chemical oxygen demand, micropollutants, and antimicrobial resistance. For micropollutants, there are already models available to model the removal of micropollutants, but to my knowledge, there are no models for antimicrobial resistance removal. I think it would be interesting to model the removal of antibiotic-resistant bacteria and genes based on the raw water concentrations of antibiotic-resistant bacteria and genes. Now I come to portable reuse. Portable reuse is a practice which is being used more and more. In this slide, you see The indirect potable reuse, the major indirect potable reuse projects. It's the first three are the most prominent one. Orange County, a very big facility, nearly 500,000 cubic meters a day. Tourelle, Belgium is also very interesting, started up already in 2002. Singapore has already 5 new water plants, and the next year another plant will be started up. Now to direct potable reuse projects. The difference between direct potable reuse and the indirect potable reuse is that indirect potable reuse employs an environmental buffer as an additional barrier. And in the direct potable reuse, Windhoek was a pioneer. They started up the old Korean Gap water reclamation plant already in 1968. In 2002, the new Korean Gap water reclamation plant was inaugurated. Another example is Big Spring in Texas. Blending operations started in 2013. I would like to mention also Cape Town. It will be the largest facility for DPR in the second phase with 70,000 cubic meters a day. It's in the design stage, expected startup 2027. And in Windhoek, there will be a second facility, DPR2, expected startup in 2028. This leads me to Namibia. As you know, Namibia is in the southwest of Africa. Windhoek is located in the Central Highlands between the Namib and Kalahari deserts. It's a very dry region, and potable reuse is essential, I would say. Here, a simplified direct potable reuse scheme. The raw water is domestic sewage, which is treated in this Gamam sewage treatment plant. The secondary effluent, not indicated, polished in maturation ponds. The effluent of the maturation ponds is the raw water for the new Korean Gap water reclamation plant. A maximum of 21,000 cubic meters a day is pumped directly into the drinking water network and blended with treated dam water and groundwater. The process, simplified process flow diagram. First stage, pre-ozonation for pre-oxidation, pre-disinfection, microflocculation, then enhanced coagulation. The particles are removed by dissolved air flotation. Turbidity from dissolved air flotation is removed by dual media filtration. Then we have main ozonation for main oxidation of micropollutants. Then main disinfection of protozoa, virus, bacteria. And there is also some cracking of dissolved organic carbon, which is made biodegradable. This biodegradable DOC, dissolved organic carbon, is removed by biologically activated carbon filtration. And then we have activated carbon adsorption in order to remove residual micropollutants. As last physical barrier, we have ultrafiltration, and then chlorine, safety disinfection and stabilization with sodium hydroxide. Modeling of micropollutants and antimicrobial resistance, I would say, is also interesting for such plants, in particular for designing them. In order to give you a better impression of this facility, I show you this slide. We have here the buildings, the first building, pre-ozonation, coagulation, flotation building, dual media filtration, main ozonation, activated carbon, ultrafiltration. There's a separate building for research and development, and in this building, not indicated, is the control room, which can be seen in this slide. It shows the process surveillance with the SCADA system, and another photo is the ultrafiltration maintenance. Yes, Windhoek had regular droughts. This slide shows the drinking water supply before and in the last phase of the 2015-16 drought. You can see before the drought, 79% treated dam water, 17% reclaimed water, 4% groundwater. And during the drought, the dam practically was empty. Only 3% could be supplied, and the strategic reserve groundwater had to be used. It was increased to 66%, and reclaimed water was nearly 1/3, and this is a very important contribution to the water supply. And what also has to be mentioned, the quality of the reclaimed water is superior to that of the treated dam water. It's much better. So I would say direct potable reuse has been essential for the social, economic, and environmental development of the city. And you see in 1990, the population was 140,000, and in 2023, nearly 480,000. Now, the conclusions: water reuse and recycling is mainly driven by water shortage and subsequently by economic and supply security reasons. Water reuse is cheaper than other options, such as seawater desalination. The overall water supply security is boosted, very important. Concentrate management is gaining in importance. The environmental impact can be substantially reduced, for example, by treating RO brine. In our view, the modeling and integrated assessment have a high future potential to improve treated water quality and reduce OPEX, operating expenditures. Finally, it can be concluded that water reuse is a key element in social, economic, and ecological sustainability. I thank you for your attention.
Thank you very much, Joseph, for this interesting presentation. I want just to remind the participants to state your questions in the question and answer session, and we will collectively respond to these at the end. And then the next presenter will be Giacomo Belandi. So, hi, Giacomo. Thanks for joining. Hello. And actually also thanks for pulling this initiative. So Giacomo is working for AM team, and he will present on process modeling today. The floor is yours.
Thank you. Thank you, Marianne. Thank you. And thanks for the support in organizing all of this. So indeed, I will be very brief, introducing you to the process models or the use of process models for the topic of today, for the water reuse. So as Joseph showed, there are a huge number of process unit treatment steps required for each of the water reclamation plants. And for each one of these process unit, there can be a process model to represent its behavior, to answer the key questions around its operation or its design, or actually all questions across the technology life cycle. So in this slide, you can see the main 4 pillars in which a process model can help in a technology life cycle. It goes from R&D on the far left, but also in the planning stage when a feasibility study is necessary. Is this technology applicable, and what would be the cost and the feasibility of building this ozonation plant rather than UV peroxide or UV chlorine or a peroxone? application rather than other treatment units. Or in the design stage, when we select the technology, we say, okay, this is what we need to treat this water stream and reach the water quality objectives. Then we want to size the reactor and define the chambers and define the dosing and the mixing in this reactor using both the chemistry and the hydraulics concepts. And finally, the process models can help us in operating that process unit, that plant, or that installation. So monitoring real time, but even if it's not real time, supporting the operators in the decision of every day on how to drive the installation in order to keep the water quality at the targets and safety, and also safeguard the OpEx. One example of a process model, it's a mechanistic model that we developed in-house. It's called Amazon, and it's applied in different plants here. It contains ozone kinetics and advanced oxidation processes that describe the degradation of micropollutants and the formation of byproducts. So to predict what is not measurable online or very fast by the normally available analytical techniques, then you apply a mechanistic model to understand what happens, what is the reaction resulting from a certain ozone dose to a given water matrix, for instance. So it's one example of a mechanistic model or a process model. And the process model, the mechanistic part of it, can be included in a process layout. So we represent the installation, and in this case, it's a virtual piloting example. So the representation of a pilot installation for ozone peroxide and hypochlorite injection to control bromate formation at different ozone dosages. So here the question was, what are the control strategies and the mitigation strategies around bromate that we can apply in order to remove micropollutants and minimize bromate formation? So the HRSD used the model to, we calibrated with them and validated the model with their data, and they're currently using the model to test alternatives to save time in the piloting. So without running all of the experiments in the list practically, but running a large part of them through the virtual representation of their installation and taking decision faster. Now this is going in the next step, and what we're going now is to design the help to support this design in the decisions of design of the ozone installation. And this is the second example that I'm bringing you in here, in which on the left side you have an original design, which is forming a certain amount of byproduct that you want to minimize. And on the left side, you have an optimized design in which you improve the inlet distribution, the dosing of the ozone, and the diffuser distribution in order to minimize the byproducts formation and keep the water safety. And this is including, it's an example that is including hydraulics with a kinetic model for ozonation. So it gives you spatial 3D information on how to optimize the reactor. And the third example that I'm bringing very briefly, it's an online operation of a process model. So this is a peroxone UV peroxide installation for indirect potable reuse. So it's a real-time prediction what you see in here of bromate formation. We cannot share the absolute numbers for confidentiality, but you can see over a very long period of days, actually years, different testing have been done. These have been fed into the model, and this could reproduce the bromate with higher frequency, higher information than what was measured. And from here, we could develop improved operational strategies for both the ozone installation at the top and the UV installation. So in orange, you have those applied in reality at the installation, and in blue is what the model suggested that could be a more effective strategy to reduce OPEX and improve and maintain the water quality targets. So, and with this, I pass the word on the next speaker, actually to Marianne. Thank you.
Thank you very much, Giacomo. Yeah, I will right away pass the word on to Eberhard, our next speaker. He's a professor at ETH, and I would say he's one of the people who actually has experience in both this world, in the modeling and the water reuse one. Eberhard, the floor is yours.
Yeah, Giacomo, you have to stop sharing. Excellent. Thank you very much for this opportunity. So I'm really happy to be able to follow up on Joseph and Giacomo because both of them told you that mathematical modeling is really helpful when it comes to water reuse. But the focus of my 5-minute blip is on microbial risk. And the main message of this quick presentation is that the typical conventional process engineering type models will not be suitable to answer the questions that we have available in microbial risk. So why am I making this point? When we are talking about conventional modeling of processes, you might think of a system like this. You have a treatment unit, and then on the left-hand side, many of you it will look familiar. You have an activated sludge model. You have certain state variables, and luckily, the state variables of this mathematical model are also the aspects that the treatment plant operator, that the design engineer, that the scientist is interested in. So the nitrogen species, the organic carbon. So what now happens if the questions get more complicated? If we're thinking of organic micropollutants, Giacomo just made a case, well, you need to start tweaking the model, but it's already not so straightforward anymore. You cannot have a state variable called organic micropollutants in this. And the point that I'm trying to make is that it simply is not useful or feasible to say, well, now let's have another state variable that could be called microbial safety. How come? In the next slide, I will introduce you to the requirements that treatment plants have to meet for water reuse. So here's the slide. So for, in this case, agricultural irrigation in the European Union, you have tables like this, and this table has information on organic carbon as BOD or suspended solids. And then it also has a parameter that's associated with hygiene. E. coli, number of E. coli that you quantify per 100 milliliters. The problem is, if you have a sample that significantly exceeds this number, you probably have a water that's not safe for water reuse. The problem here is that if you have water that has much less than these indicated 10 or 100 or 1,000 E. coli per 100 milliliter, you may or may not have safe water. The problem is that E. coli is simply an indicator. If you have E. coli in the water, then you have the problem that you have fecal contamination. But the E. coli itself is not the problem. You have pathogenic viruses or bacteria or protozoa that you have in the system. So modeling E. coli as a new state variable would not be sufficient. So if we're now thinking of the question of modeling, understanding, quantifying microbial safety, you need to take into consideration a number of factors. You need to understand or model or predict the amount of pathogens in the input water. That has to do with the kind of water that you're treating. It has to do with scale. I'll have an example in a minute. Safety then depends on the type of treatment that you're using. And safety ultimately depends on the way that you're using this water. If you're using the water for toilet flushing, or if you're using the water for showering, the exposure will be different. So these are 4 factors. And the last factor that is important to mention is the acceptable exposure, so the acceptable pathogen concentrations, the acceptable risk of infection. And also there are a number of different choices that you can make. 5 factors. And so these are color coded, and I will use this color coding in the next slide that has a complicated equation. I will not talk about the equation. I will talk about the color coding. So this is the quantitative mathematical model for quantitative microbial risk assessment. And in quantitative microbial risk assessment, you have a number of factors related to the specific pathogens that we could be interested in. We have a factor that's quantifying the volume ingested, again, different for toilet flushing or for showering. You have a factor that's looking at the log removal, so the percent removal that you can achieve with a particular treatment system. And then on the left-hand side, you have the risk of infections. So this equation is now relating all of these different factors. So this is now the model. In the next slide, what I'm showing you now, it's a complicated slide, but I have a single very simple message in this. If you want to determine the required log removal, and so these red boxes in here refer to the required log removal for protozoa, for bacteria, or for viruses, then the required log removal depend on the specific type of virus. So rotavirus requires more removal than norovirus, for example. It depends on the type of reuse application, if you're using it for shower or for hand washing or for toilet flushing. And it also depends on scale. So these log removals here are all shown for a large system, an apartment complex with 1,000 people. If you do the same quantitative microbial risk assessment, so the modeling, you see that the log removal that's required is very different. Essentially 0 for all of these different pathogens except for norovirus. So the point that I'm making is it doesn't make sense to simply look at bacteria in general or E. coli as an indicator. The specifics of modeling the input dynamics, input characteristics, the exposure, and in this scale also, in this slide also the scale determines how and what kind of treatment you need. Giacomo told you about detailed process modeling of how a system can perform. This modeling tells you about the required performance that you need for safety. So the point that I'm making is simply adding more state variables to mechanistic models will not be sufficient, because we cannot directly model hygiene. What we need are models, or it's really combinations of models that will help us understand removal or inactivation of different pathogens, help us model pathogen loads in wastewater, and help us model really a number of other factors related to uncertainty, exposure, monitoring, and also failure modes that you might have with such a system. So modeling is really important. You really need to start thinking from very different directions than your typical process model. Thank you very much.
Thank you very much, Eberhard, for this very brief insight into a new type of modeling. I would like to hand over right away to Luca. Luca is a PhD student at Politecnico of Milano, and I'm very excited to hear a presentation about impact assessment models.
Okay, thank you, Marian. And can you confirm me that you see and hear me? Okay.
Yes, we do.
Okay, so good afternoon, everyone. And so in these previous presentations, we saw practical examples of showing the potential of different modeling approaches when they are applied to the water use system. While right now, I would like to give you a brief overview of the models that are available for evaluating the impacts related to the wastewater use, but in agriculture, and particularly focusing on how they can be integrated. So if we think about the agriculture, the common practice is to derive water for irrigation from the surface water, but in this same surface water, typically many wastewater treatment plants discharge their effluent. So basically, we have an indirect reuse, which is de facto implemented without any impacts evaluation. We started talking about impacts evaluation with the direct reuse. In particular, we talked about positive impacts, which are similar to the ones that were illustrated previously by Joseph. So typically the recovery of water, but in case of agricultural reuse, also the recovery of nutrients. But in both direct and indirect reuse, we have also a series of negative impacts, which are commonly characterized by long-term effects. Think, for example, to the salinization of soil and crops, or the environmental compartment cross-contamination that can lead to environmental or human health effects. Eberhard just explained us the challenges that we have in modeling the microbial water safety, but we have also, for example, a chemical risk which needs to be assessed. So in this complex system, the question is if we do have available models for assessing these impacts, and most of all, how can we integrate them for supporting the decision-making process? For example, we know that implementing reuse in a wastewater treatment plant implies an allocation of resources, so a cost. So how can models support us in choosing the best wastewater treatment plants for implementation? Or again, if we have to monitor their use system, how can we identify the most vulnerable compartments or the most hazardous substances to monitor? So starting from the first question, if we analyze the most recent literature, focusing on those articles that model the impacts of agricultural reuse, we can recognize three main characteristics, which are the compartments that are involved in their use, the models adopted, and the variables that are targeted by these models. And in particular, we can distinguish between quantity-based models, which typically evaluate the impacts related to the water volume, and they are usually typically to model big-scale systems. Or on the other side, we have quality-based models, which instead consider the impacts related to the contaminants contained in the wastewater, and they are more specific for single compartments. But when it comes to model the wastewater use system, they are not always integrated appropriately. So for example, if we want to select where to implement reuse, what is typically done is to adopt quantity-based models. And they are well integrated among them, and typically their main aim is to optimize the water volume distribution within a system, considering different water use scenarios. But on the other side, they typically neglect the quality aspect. So we wonder if it's really necessary to consider the quality of wastewater aimed at reuse. To answer to this question, we focus on a study that attempted to prioritize the wastewater treatment plants in which implementing reuse by integrating both quantity and quality aspects. So specifically, a techno-economic model was developed considering among the inputs both quantity variables, but also quality variables related to the wastewater treatment plants, and matching them with the characteristic of the surrounding territories. And to obtain in return positive outputs, such as the savings in terms of primary fresh water or mineral fertilizers, but also the avoided greenhouse gas emissions, together with negative outputs, such as the crop yield loss due to salinization. All these outputs were converted into economic terms and summed together to evaluate the economic feasibility of the reuse implementation. This model was applied to a set of wastewater treatment plants. In particular, inputs data were collected from 95 wastewater treatment plants, and they were classified based on their size, nutrient removal train, and type of surrounding crops. In this way, it was possible to evaluate the class of wastewater treatment plants instead of the single plant, in order to enable the identification of the system characteristics that make most profitable the reuse implementation. So, for example, I will try to guide you through this graph, but from this graph we can see the economic results that are reported, differentiated by the class of the wastewater treatment plant, and we can see from the bars how the different contributes of positive and negative outputs are distributed in the different classes. While if we look at the purple dots referring to the potential annual savings, we can observe that the type of crops are more relevant in determining the economic savings compared to the characteristic of the wastewater treatment plants. For example, if for some specific type of crops, such as carrots, for example, the reuse implementation results not economically feasible at all. And so we can conclude that the quality aspect does matter, and especially when it is associated with the related crop requirements. While if we want to understand where to focusing the monitoring efforts, this is usually done instead with the quality-based models, and they are largely adopted to address the effects on soil and crops, and they are typically used to evaluate the concentration of contaminants of interest in these two compartments. But we can see that the aspect of the risk assessment application is commonly overlooked. And even if it would provide an additional information to the concentration, which is the toxicity level of the contaminants. So focusing on the studies addressing the human risk, the risk assessment, we can see that most of the studies assessed the risk in terms of human health, while very few evaluated the environmental and antibiotic resistance development risks. But we can see that in the case of indirect reuse, those two risks are inherently present. So what we've done is to focus, like here, I show you the distributions of the estimated risks for different chemicals obtained by those studies that estimated only the human health risk in case of indirect reuse. And we can observe that all the box plots are well below the risk warning thresholds. So we would conclude that no risk is present. But if we also calculate the environmental and antibiotic resistance development risks, we can see that the risk warning threshold are overcome in most of the cases. So only considering human health risk would have made us underestimate the overall risk. So to wrap up, we can conclude that models for evaluating multiple impacts are currently available, and they just need to be properly integrated. Then the quality aspect cannot be neglected, and especially when it is associated with crop requirements, and that it is necessary to integrate the risk assessment procedures in a One Health perspective, so not only considering human health, but also the environment. So I would like to thank you all for the attention, and I would also like to thank you, my research group at Politecnico, which is the Safe Water group that support me in this work. Thank you.
Thank you very much, Luca, for the insight into your work. I would ask to all the presenters to enable your videos that people can see you. That would be great. There were no questions actually in written form submitted, but I'm pretty sure there are people who do have questions. So please raise your hand if you have a question and profit from having all these experts here. If not, I picked up one topic that Josef was actually mentioning about the removal of antimicrobial resistant bacteria. And I wanted to ask Eberhard his thoughts on that. I mean, so Josef said that there are no models existing. What do you think, like what would be needed? And yeah, your estimation.
Thank you, Marianne. I think a common thread in all of the presentations was that one of the difficulties when we're looking at water reuse is really identifying the compounds that we're interested in and the relevant questions that we can ask. So I had a presentation on microbial safety. I didn't even mention antibiotic resistant bacteria. So thinking about what else should be included as relevant. In the microbial risk modeling, most of the risks that are being modeled are acute risks. Of course, then antibiotic resistance bacteria and their genes is definitely also relevant, exactly what Luca was presenting. What it means for me is there will not be one super model that includes everything, because there will always be something else. So you always need to be on your toes and think about, should I also answer this question and neglect something else? That's one aspect. And then getting relevant data and relevant input per model. So this is much more difficult than typical treatment plant modeling.
Okay, thank you. We actually have a question, Hadel. Can you introduce where you're from and yeah, your question, please?
Okay, thank you very much for this nice and insightful webinar. My name is Hadid Hosni. I'm working at IHE Delft Institute for Water Education in the Netherlands. Actually, I'm a lecturer and researcher in wastewater treatment and reuse. So it is really very relevant to my domain. I have two questions. Before the questions, I fully agree with Eberhard that we cannot find one comprehensive model that cover all target contaminants, microbial and micropollutants, and so on. So it comes to priority. So what is important for you according to your location first, because reuse is location specific, and second, according to the purpose of reuse. It is for agriculture, direct reuse, indirect reuse, and so on. So my first question is about modeling to Gaia Como, sorry if I'm not pronouncing it well. I saw in your graph that you have one contaminant, which was the bromate, and the concentrations are measured with microgram per liter. But I wonder if we are going to select another micropollutants, like for instance, carbamazine, where the concentration should be measured in nanogram per liter. Is your model is valid for such measurements for low scale, or it is a bit restricted to the microgram per liter? So,
yeah, thank you for the question. It's very important indeed. So I only showed due to the restricted time, the bromate story, which is a byproduct, and it ranges around the microgram per liter, the worry, let's say, right? The advantage of the models is that numerically you can go very low and you don't care about the analytical limitations, right? Apart from the calibration part. For micropollutants instead, like pharmaceutical products or like agriculture products for fungicide, herbicides like this, We have a list of about 100 micropollutants that are included in the model and are running in dynamic with this simulation, and some of them indeed need to be predicted at the nanograms per liter. What we typically approach to help the visualization of it, the approach is to look at the relative removal. So the exposure to a certain oxidant will provide a relative removal in time, and then you visualize that in terms of a percentage of removal for that specific contaminant. That's how you visualize all of them together. But also the absolute number can be indeed predicted.
May I ask you a follow-up question? What is the range for the modeling? So what is the concentration range for modeling? Out of my experience in the lab, I did modeling, but very basic, using ANOVA Design Expert, using the RSM, the Response Surface Methodology. And what I found that any modeling or using empirical equation for the prediction for concentrations of micropollutants below 1,000 nanogram per liter is not accurate. So it can really be very accurate model when you model something above the 1,000. And for instance, most of the micropollutants are below 500 nanogram per liter in the treated effluents that generated from wastewater. So I wonder what's the range that you have in your model?
So it strongly, as you know, it strongly depends on the knowledge around the reactivity of the micropollutant, of the specific molecule. You might have a very good knowledge around carbamazepine. You might have a little bit less knowledge around irbesartan, for instance. The other thing that you mentioned is that empirical models have this strong limitation, right? Because they're strongly linked to the limitations of the analytical method. Whereas mechanistic models have less of this limitation, because the mechanism itself, in principle, with this, if the standardized conditions are maintained or adjusted, I'm talking about temperature and pressure and pH of the test conditions, or describe how they vary in those domains, then you can more accurately predict their degradation in the nanograms or even lower concentration. But of course, you have still a strong relation with the analytical methods.
Okay.
Herbert, you want to add something?
Well, I just want a follow-up thought. So we have now 87 modelers in this chat or in this webinar, and I think we said there are different models for different questions. So if we now have everybody going loose, doing their favorite pet topic, I think we would be wasting a lot of brain power. And I think Joseph had a really important slide in his presentation where he said, well, economically, here are the relevant questions. And there are a lot of things that Joseph does not care about and some things that he cares very much about. So I think having a joint process of identifying what is important, and safety is important, and also Luca mentioned this in terms of microbial or chemical safety, but also economics. So I think that the art is really now in understanding where to focus and where to let go, even though this is your favorite topic that you've always have, that you have a lot of experience in.
Yeah, agree.
I think that was actually a really nice final word from you, Eberhard. We actually already exceeded the time, and I also see no further questions. There is just one small last thing. So I wanted to advertise like the deadline that is already tomorrow for some conferences on actually resource recovery in water. So there is one deadline tomorrow. Then next Monday, there is actually another webinar on good coding practice. And then there is also the conference that is next year, where the deadline is on the 5th of May. that Joseph actually mentioned in Cape Town on reclamation and reuse of water. So that might be interesting for the participants here. Yeah, and with this, I would like to thank everybody for participating. I think it was really nice to come together. There is for sure more discussion needed. So yeah, let's hope there's a follow-up at one point.
Yes.
Thank you very much.
Thank you. Thank you all.
Thank you. Bye.
Everyone.